So in the last class, we looked at both the conversions, that is converting a regular expression into NFA or NFA, and then also converting NFA or DFA into regular expression. The previous step, that is converting regular expression into NFA, was part of the first lemma. That is, given a regular expression, the language that is being described by the regular expression is a regular language. So how to prove that? You should be able to build an NFA or DFA for this particular language which is being represented by this regular expression. So we proved the lemma and then we gave example of how to convert any regular expression to NFA. The next one is a precursor to the second lemma. That is, given a regular language, you will have a regular expression describing that regular language, which we are about to prove. But before that, if you are given a regular language, it means you are also given an NFA or DFA, right? So if you can convert any NFA or DFA into a regular expression, that is equivalent to saying that you can convert a regular language into a regular expression. Okay, so this is a precursor to second lemma. We also looked at generalized, not generalized, a complex case of NFA where we are reducing one state at a time and we are converting that portion into a regular expression, right? And finally, we will be left with only two states, and the regular expression on the transition between these two states will be the equivalent regular expression for this NFA. Okay, so we saw that. Now we will start proving the second lemma. Okay, so earlier we proved the first lemma. Today we will prove the second lemma. So what is the second lemma? If a language is regular, then it is described by a regular expression. Okay, so what is the proof idea? If you have a regular language, then it means you also have an NFA or DFA for that corresponding regular language. So if you can convert this NFA or DFA into a regular expression, then you have proved that each regular language also has a regular expression. Okay. So if A is regular, then it is recognized by a DFA or NFA if we can show how to convert any DFA into a regular expression, then we can in turn prove that any regular language can be described by a regular expression. So here we will show a stronger proof, not just converting any NFA to a regular expression, but we will directly convert a DFA to regular expression. Because if you are able to convert a DFA, it is also like converting NFA. But if you are able to convert only NFA, it's not like converting DFA, right? Because every DFA is NFA. The other way is not same. Okay, so we'll directly show how to convert DFA to regular expression. So the proof has two parts. The first part is converting DFA into something called a GNFA. We'll look at what it is. A GNFA is a generalized NFA. And the second part is converting GNFA to regular expression. So first we define GNFAs. GNFAs are simply non-deterministic finite automata wherein the transition arrows may have regular expressions as labels instead of only members of the alphabet or epsilon. The GNFA reads blocks of symbols from the input at a time. So this is the main difference. There are a couple of other differences which we will look at in a while. But the main difference is a GNFA reads regular expressions directly. NFA or DFA reads one symbol at a time. From one state to other state, if you have to go to, you have to read one symbol at a time, right? You can't read two or more symbols at once in DFA or NFA. Whereas in a GNFA, you can read a block of symbols. You can read more than one symbol. You can read a string, an entire string at a time to move from one state to another state. So for instance, say if there is, say, some transition from Q1 to Q2, maybe something like AB star. Okay. In DFA or NFA, you have only one symbol as a transition label, but here you have regular expression. So what this regular expression stands for? Normally regular expression stands for an entire language, but here what it indicates is any string from this language. Basically AB star indicates language like A, AB, ABB, A triple B, and so on, right? So any of these strings, if any of these strings comes here as input, then you can move from Q1 to Q2. Not the entire language, but any string from this language. Now, similarly, say from Q2 to Q3, if you get input, say like A, B, B, A, something, right? Then it will move from Q2 to Q3. So if you have an input string like A, B, B, say A, B, B, A. Now, it reads this to go from Q1 to Q2, and it reads this portion to go from Q2 to Q3. Now, it may split in some other way also, like if it splits only like this, and this has two parts, then it won't go from Q1 to Q2. Sorry, this will go. If it splits like this, then it goes from Q1 to Q2, but from here it won't go from Q2 to Q3, right? Because it should be ABBA only. But it does not matter. At least if one way of splitting takes you from one state to the other state, and by continuing this process, if you end up in a final state, then the entire string will be accepted. There can be million ways of splitting a string. If at least one of these ways will take you towards the final state, that is fine. It's not necessary that every way of splitting should take you to the final state. Okay, so in this case, at least one way is there in which you can move from one state to the other state. But there may be strings where not even one case you will find. No matter how you try to split it, you cannot move from one state to the other state. For instance, if a string starts with B, anything, say BA, BA, whatever it is. Now, this will not even go from Q1 to Q2. It has to start with A, so it won't go anywhere. So no matter how you try to split it, this string will not be accepted. Okay, so the point is, it is not reading one character at a time, it is reading a substring at a time, an entire chunk of symbols at a time. That's what a GNFA is capable of doing. So you can give regular expressions themselves as labels to the arrows. That's the only difference between NFA and DNFA, GNFA. Okay, that's all. That's the main difference. There are some other slight differences which we will look at. So let me move on to the next page. Use this page only. So this is an example of a GNFA. We'll come back to it in a while. So let me list down the important conditions for something to be called a GNFA. First, the start state has transition arrows going to every other state but no arrows coming in from any other state. The second condition is there is only one accept state and it has arrows coming in from every other state. But no arrows going to any other state. Also, the accept state is not the same as the start state. And the third and the final condition is except for the start and accept states, one arrow goes from every state to every other state, and also from each state to itself. Okay, so these three are the main conditions. Basically, there should be only one start state and one accept state, and start state should have only outgoing arrows and no incoming arrows. Accept state should have only incoming arrows and no outgoing arrows, and all the intermediate states should have outgoing arrows to every other state, including itself. That's all. So that is how, if you look at this diagram, it will also be the same. So you have start state, no incoming arrows, only outgoing arrows, and to every state, the intermediate states as well as the final state. And the final state, there is only one. It has incoming arrows from every state. This one, and also the start state. Okay. And these are intermediate states. They have outgoing arrows to other intermediate states and anyway the accept state. And they also have self loops. Okay. Now, in case you don't normally have a transition between two states, then you sort of represent it using phi, the regular expression phi, which means there is no transition. You cannot go from one state to the other directly. So that's what this phi indicates. But you should have an arrow. Whatever the label is, you should have an arrow. That's what GNFA is about. Okay. So now we'll see how to convert a DFA into a GNFA. And the example which we discussed in the last class, it's not exactly a GNFA, because if you see this state does not have a self loop, and also this state does not have an outgoing arrow to the accept state. Okay, this is just an example which I just gave so that I could show you how to sort of condense a state diagram. That's all. This is not technically a GNFA, nor it is a DFA. This is just an example to mainly show you how to condense an NFA state by state. Okay, so that's one of example. We will not look at any such example from now on. We will just look at DFAs and how to convert them to GNFAs and then convert them to regular expression. Okay. So process for converting a DFA into a GNFA. First, we add a new start state with epsilon arrow to the old start state and a new accept state with epsilon arrows from the old accept states. And second, if any arrows have multiple labels, we replace each with a single arrow whose label is, can you fill the remaining? Union of these labels, right? So for instance, if I have some arrow like AB, then I'll replace that with A union B. And it need not be just AB, they can be regular expressions as well. So R1 union R2, if there is R1 comma R2, then we will replace it with R1 union R2. Okay. Whose label is the union of the previous labels. And finally, we add arrows labeled 5 between states that had no arrows. Okay, so this is the first step, that is given a DFA, you should convert it to GNFA. Now the second step is converting the GNFA to regular expression. So process for converting GNFA into a regular expression. So say that the GNFA has k states. If k is 2, the GNFA has a single arrow that goes from the start state to the accept state. The label of this arrow is the equivalent regular expression. If k is greater than 2, we construct an equivalent GNFA with k minus 1 states. We repeat the above step until it is reduced to how many states? 2 states. You should be left with only one start state and one accept state. That's it. So if you have more states, you continue reducing it, reducing one state at a time until you are left with 2 states. So let me depict it as a diagram. So this is an example. Suppose you start with a 3-state DFA, right? So you will add a new start state, a new accept state. So you'll get a 5-state GNFA. Now you will start reducing this 5-state GNFA one state at a time. So you will convert it to 4-state GNFA, then 3-state, then 2-state, and you will stop there. So whatever is the regular expression on this 2-state GNFA, that is the equivalent regular expression. That's all. Okay. So this is just an example. Now the penultimate step in the above process is the crucial step. That is constructing a GNFA with k minus 1 states from a GNFA with k states. Below is the procedure for that. So constructing an equivalent GNFA with one fewer state. So suppose we have three states, say Qi, Qj, and a third state called Qrip, because this is the state that we will rip apart later. And there is a regular expression from Qi to Qrip, say R1, and there is a self loop on Qrip with regular expression R2, and there is a regular expression from Qrip to Qj R3, and finally there is a regular expression from Qi to Qj, that is R4. Now if we remove the Qrip state, we are left with only Qi and Qj, right? Now what will be the regular expression on this transition between Qi and Qj? Yeah, so it will be R1, R2 star, R3 union R4, right? So basically we are condensing this portion. We are removing this state and replacing it with a regular expression. Okay, so this is the before state and this is the after state. After state in the sense the state of the entire diagram. So again you need to notice here we are able to replace this particular state because this is part of a directed path. If this were not a directed path, then you cannot replace it, then you cannot remove it. So again, this is an example where the concepts which you learned in chapter 0, they come in: graphs, paths, directed paths, cycles, all those things. So here all the arrows are pointing in the same direction. That's why you can replace this. You will get an order of the regular expressions. So first R1 will come, then R2 star will come, then R3 will come. If the direction of the arrows were different, then you cannot do this, right? So implicitly it is also being told to you that you cannot remove any and every state. You can remove only those states which are part of a directed path. Okay, so yeah, so let's continue. We make this change for each arrow going from any state Qi to any state Qj including the case where Qi equal to Qj. So what do we mean by that? It's not necessary that you should always have three states. Sometimes you can also have a case like, okay, there are two states and there is an arrow like this, and there is an arrow, a self loop like this, and again there is an arrow like this. Okay, so you can think of this as R1, R2, and R3. Now you will remove this state with R1, R2 star, R3. Okay, so in this case, what is Qi, Qj? Both Qi and Qj are the same state. All right, so sometimes they may be different, sometimes they may be same, but in both cases the same logic will apply. And can start state or accept state ever be QRIP? No. Why? They can be Q8, QJ. That they can be. Can they be QRIP? No. Why? Exactly. It should be an intermediate state. There should be an incoming arrow, there should be an outgoing arrow for something to be QRIP. Otherwise, you can't rip that state. What will you replace it with? And where will that regular expression arrow go to? Right? So start state and accept states cannot be QRIP. They can't be ripped because they either only have incoming arrows or only outgoing arrows. They don't have both. So only those states, and obviously they are intermediate states, those which have both incoming and outgoing arrows will be part of a directed path, and they can be ripped apart and be replaced with a regular expression. Okay, so everything is neatly formalized. So you, even if you want to, you cannot replace start state and accept state with a regular expression. They will be left finally in this entire process. Okay. And finally, the new machine recognizes the original language. Why? Because at every step we are maintaining the equivalence. The machine which we are building from this step to the next step is equivalent to the current machine. Okay, so finally whatever machine you are left with, the new machine, that will replace the that will recognize the original language. Okay, so now let's look at the formal definition of a GNFA. So a generalized non-deterministic finite automaton is a 5-tuple that is Q, sigma, delta, Q start, and Q accept. Should I put Q accept in brackets, set brackets? Not necessary, because this machine will have only one accept state. So there is no variation in this. So in the definition also, you need not worry about having a set of accept states or not a set of accept states. There is only one accept state. So you just write its name. Like, why are we not putting start state in set brackets? Because we know there is only one start state. So now we know there is only one accept state, so you don't need set brackets for that also. Okay. Where Q is the finite set of states. Sigma is the input alphabet. And delta. So what will be the input and output of the transition function? Hmm? Hmm. Hmm? Output will be one state. Okay. Yeah, that is fine. But the point is, it may not be one state, because you see, when you combine multiple regular expressions, I mean multiple symbols, sometimes you may end up with the same regular expression. So it can be like something very simple. Suppose, how do I say? Say Q1. Suppose yeah, I'm not sorry, I'm not getting the correct example right now. Basically, hmm? If two outgoing arrows have the same label, then we will combine them. Yeah, thanks for the clue. Now I got it. So suppose you have three states. So suppose this is AB, and suppose you have another two states, and suppose this is BA. Okay. I'm sorry. This is fine. Okay. Again, I can't think of example. I thought I got it, but so the point is, for the same regular expression, it may happen that you may need to go to more than one state. Okay, something simplest. Basically, suppose you have more than one arrows with 5. Okay, which means basically you can't reach Q2 and Q3. You may reach Q4 with some regular expression. Okay, but for Q2 and Q3, you have the same regular expression 5. Now, if you give this state Q1 comma 5, your output will be not one state but a set of states, right? Q2 and Q3. But we don't want this. We want one regular expression between a pair of states. In the sense, this will happen. This we can't avoid. Okay, but we want the output to be one unit, like one, not even a set. We want the output to be one state. So rather than that, but that is not possible. It's not one state. It can be more than one state for the same regular expression. So what we will do, rather than mapping a state, and a regular expression to a set of states, because it will be a set of states, we can't avoid that. What we will do, we know that between any two states, like maybe Q1, Q2, or whatever, any two states you take, you will finally condense all the arrows into one regular expression. If you have multiple arrows, you will perform a union. So you will get one regular expression. So finally, between any two states, you will have one arrow with a regular expression. So you take these two states as your input and a regular expression as output. Because regular expression will be only one. There is only one arrow between any two states. If you have more arrows, you will condense them to one arrow. So finally, you will be left with one arrow. So you will not have two or more arrows between given two states. If you have two or more, you will condense them to one. That will be a regular expression. So now the mapping is simple. Input is two states, output is one regular expression. Okay, so this is again a function. So now tell me what is the domain and range. Okay, Q cross Q is the domain, and maybe set of regular expressions is the range. Yes, this is different from the previous, like DFA or NFA. This is different. In the previous cases, we know that for a given state and a given input, in DFA case, we'll get only one state. So that is Q cross sigma to Q. In the case of NFA, we know for a given state and a given input, we will get a set of states. So that is Q cross sigma to P of Q. But in this case, we know between any two states, there will be only one regular expression. So this is Q cross Q to R. But there is a slight variation in the domain. Can you guess what that is? Yes, exactly. So you see, this Q cross Q is basically telling me this first element is the source, the second element is the target, right? So between this source and this target, you have an arrow on which you will get a regular expression from this. But in the source, can all the states be the source? All the states can be source except accept state. Accept state cannot be a source. You can't have an outgoing arrow from the accept state. Okay. Similarly, all the states can be target except start state. So you can't have start state in the target states. So we will modify this by saying the first Q is Q minus Q accept. This thing cross Q minus Q start. Okay, now this entire thing will map to set of regular expressions. Okay, so this is the transition function. Where R is the collection of all regular expressions over the alphabet sigma. If delta of qi comma qj equal to R, where R belongs to R, the arrow from state qi to state qj as the regular expression or as its label. Okay, and finally Q start is the start state. And Q accept is the accept state. Okay, any doubts? Yes, no, see, 5 arrows, yes, from that you will have a 5 arrow to final state. No, 5 means it won't. Even if you come with a string to the dead state, the moment you do 5, finally it will be 5 only. R.5 is 5, it's not R. So whatever it accepts through this route is 5, not R. Okay, yeah. Okay, so still a little more portion is remaining that we will cover after the exam. So whatever we covered post minor 1 until this class is part of your minor 2 syllabus. Okay. So let's, yeah.